We are now moving on to the physics sections of science, which are split into several subject areas, and we'll kick off with electricity and magnetism. For your test, you need to know about the different components that make up circuits. So we're going to run through a list of them. First of all, the wire, which we have seen is a metal and a good conductor of electricity. Next, the battery. Now, the battery is the store of energy, which provides the push or the potential difference that gets the current flowing. Let's look more closely.
The current flows through the wires of a complete circuit and lights up the bulb. The bulb uses electrical energy, but not current. Look. The current is exactly the same before and after the bulb. We might think of bulbs as using current, but they don't. Sometimes models can help explain certain aspects. Here, the flow of negative charges in the water represent the current. The water wheel, like the bulb, uses energy as it turns. But the current before and after the water wheel is always the same. Actually, the wheel uses all the electrical energy and the current stops flowing, but none of the charges are used up by the wheel. In the same way, in the electrical circuit, the current after the bulb is always the same as the current before, but eventually the store of energy in the batteries runs out.
So for your test, you need to know that current in a conductor is a flow of negative charges called electrons, and that the current is not used up. Voltage is a measure of the force pushing that current around the circuit. Other components of circuits that you need to know about are light bulbs and switches. Let's run through how they're symbolized on a circuit diagram. So a cell or battery will look like this. And if there is more than one, you will draw two symbols to each other. The battery supplies the electrical energy. The light bulb will have this symbol, and sometimes this one. And a switch will either be opened or closed, showing whether the circuit is off or on. And if we have more than one light bulb in a circuit, in fact a series, we need a larger voltage. That's because the light bulbs create a resistance in the circuit, and the more light bulbs there are, the greater the resistance, and therefore the bigger the voltage needed. But don't forget, the light bulbs do not use up the electrical current. The current going into the bulbs is the same as the current coming out. These light bulbs here are connected in series, but they can also be connected up another way.
More than one bulb can be connected into a circuit, like this. The bulbs are said to be connected in series. When the switch breaks the circuit, all the bulbs go off. This is true wherever the switch is positioned in the circuit. This isn't the only way to connect the bulbs. The bulbs are now connected in parallel. If they were connected this way with the switch positioned here or here, they still all go off. But if the switch is put in here, then only one goes off, and the same here and here. With three switches in place and the bulbs covered with coloured filters, we have a basic traffic light.
In a series circuit, there is only one current path between the positive and negative terminals of the power supply. A switch placed anywhere in the circuit will turn all of the components in the circuit on and off, and the size of the current is the same at all points in the circuit. Increasing the number of batteries in the circuit will increase the current, but adding more components will reduce the current because there is more resistance in the circuit. In parallel circuits, there is more than one path the current can take between the terminals of the power supply. And a switch in a parallel circuit will only affect those components in the same current path. The current splits and rejoins at the circuit junctions, and remember, the current will not be the same in all parts of the circuit. But the total of the currents in the branches of the circuit is the same as the current leaving and returning to the power supply. A very typical test question would be, can you name two differences between series and parallel circuits? So the answer to can you name two differences between series and parallel circuits is, in a series circuit, the current is the same anywhere in the circuit. In a parallel circuit, the current is not the same. And point 2, in series circuits, one switch will affect the whole circuit, whereas in a parallel circuit, a switch will only affect those components in the same current path. If you weren't sure of the answer, why not rewind and run through parallel and series circuits again? The Key Stage 3 bite-sized book and the website will help you with more practice questions. The most common magnetic materials are iron, steel and nickel. And when one of these metals is magnetized, we call it a magnet. Now this is a bar magnet and the ends of the magnet are called poles. One end is the north and the other is the south, and they both attract these paper clips here. But what happens if I now have a magnet and I put similar poles together?
These 6 magnets are suspended. Move them closer together. Why? The ends of the magnets are called poles, one the north pole and the other the south pole. Bring 2 like poles together, both south, both north, and the magnetic force pushes them apart. They repel. But bring 2 different poles together, one north, one south, and the magnetic force pulls them together. They attract. Now, if I put this metal sheet between them, this could be your fridge door.
These magnets are pushing each other apart, so they must have the same pole on each.
Yeah, either both north or both south.
But when you bring them near the metal door of the fridge, it doesn't matter which pole is facing the door. Both are attracted to the metal.
Oh, yeah.
Let's move on to look at magnetic fields.
a magnet doesn't have to be touching whatever it's attracting, like this paperclip. The force of the magnet can be sensed all around the magnet, and this space of attraction is called the magnetic field. Now, the magnetic field is invisible to our eyes, so how do we see it? Well, these small pieces of iron are called iron filings, and they line up in the shape of the magnetic field. And where the lines are closest is where the force is strongest, at the ends of the magnet, at the poles. Is only part of the picture. Magnetic force doesn't just work in air. The iron filings have been mixed with oil. Drop in the magnet, we can see the shape of the magnetic field all around the magnet. The iron filings are closest together at the poles, and that's where the magnetic field is strongest. Further away from the magnet, the filings are wider apart, and that shows that the magnetic force decreases the further away you are from a magnet.
So the key points are, the magnetic field is the region or space around a magnet on which a force is exerted. All magnets have two poles called north and south, and these are the strongest points on a magnet. Opposite poles, a north and a south, will attract each other, while like poles, for instance a north and a north, will repel each other. Bar magnets are not the only things that can produce a magnetic field. Watch what happens in this next clip.
What is causing this? Well, it's a coil of wire attached to a battery. But is it the wire that's causing the magnetic field? With the battery connected, we can see the magnetic field. But if I disconnect the battery, magnetic field disappears. So it must be the electrical current that's causing the magnetic field, not the wire.
So you need that electromagnets are temporary. They are only effective when the electrical current is switched on. This means that their magnetic fields can be turned on and off. This section on electromagnets completes our unit on electricity and magnetism.
But they don't. Sometimes models can help explain certain aspects. Here, the flow of negative charges in the water represent the current. The water wheel, like the bulb, uses energy as it turns.
And a good conductor of electricity. Next, the battery. Now the battery is the store of energy which provides the push or the potential difference that gets the current flowing. Let's look more closely.
The current flows through the wires of a complete circuit and lights up the bulb. The bulb uses electrical energy but not current. Look. The current is exactly the same before and after the bulb. We might think of bulbs as using current
Into several subject areas, and we'll kick off with electricity and magnetism. For your test, you need to know about the different components that make up circuits. So we're going to run through a list of them. First of all, the wire, which we have seen is a metal. We are now moving on to the physics sections of science, which are split